Okay, so the focus of this little instructional video will be about stream deposition, deposition in general, and then something called delta formation. So there's a PDF that's attached to the same assignment, and when I open it, I'm going to annotate with Cami. And it just takes a little bit of time for it to open, but that's okay, because right now we have time. Alrighty. So I have my markup tools I could use. I could use text boxes, which I'll probably use in the beginning part. So if I just look at that first question, as the river entered the ocean, the velocity of the river. So think about yourself. If you're sliding down a slide into a pool, when you hit that water, your velocity decreases. So the velocity of the river decreases. I should spell it right? So what's cool about it, you could very easily change the font size. I'm probably going to go like 24. That's nice. I could even make it red if I wanted to. As a stop sign, it decreases. Kind of cool. Classify the particles, page 6 of the Earth Science reference table. It's at the end of this document. That would likely be found at each zone if zone A contains particles from 0.2 to 6.4 centimeters. So we're telling you that zone A, the particles there are 0.2 to 6.4 centimeters. So that's zone A. Therefore, I know zone B would be smaller than that, and zone C would be smaller than that, and zone D would be even smaller than that. So when that river enters and it slows down, the big stuff gets dropped off first. So if I look at my reference table page, if I look at my reference table page right over here, so the thing said that A was 0.2 to 6.4. So 0.2 to 6.4, I could zoom in a tiny bit. 0.2 to 6.4, that would be pebbles there. So I know that I can type in right over here, pebbles. And then zone B then would have to be smaller than pebbles, right? So zone B would be sand. So then I would put sand over here, theoretically, sand. And then what's C going to be? So here are pebbles, sand, and then I need something smaller than sand is going to be what? Oh, silt. Silt would be deposited next. And then we adjust that. And then the last one would be clay. So if you went where a river entered a large body of water, it doesn't always necessarily have to be the ocean. It could be a lake. And if you put on a scuba mask and just kind of swam outward, you would see that the particles would be very large where it first enters. And as you got further and further away from the river, where it enters the large body of water, you would see that the particles would get smaller and smaller. So question 3 says, on the diagram, place an X where you would likely find a particle with a diameter of approximately 0.005 centimeters. So now I go back to my reference table. Where would 0.005 be? Let's double check. It's 0.05. I apologize. I exaggerated. I tend to do that. So 0.05. Well, here's 0.2, and here's 0.006. So we're looking for sand, because 0.05 would be considered a sand particle. So what I'm going to do then is I could literally, it says place an X. So my sand would be zone B. So I could literally just go right here and I could just make an X. And if I wanted to, I could highlight it. I can make it bigger, 48, and I could just move it. Just as long as you're in zone B, everything is cool. Everything's good. Okay, so let's look at number 4. It says, on the diagram below, draw the overhead depositional pattern that would develop as the river enters the lake. Particles carried to the lake include sand, clay, silt, pebbles, and cobbles. You can write the names of the particles in an appropriate place in the diagram rather than drawing the particle to make it a lot easier. So if I look at that list and I compare it to here, I could see that it doesn't have boulders, so I don't have to worry about that. It has cobbles, pebbles, sand, silt, and clay. So cobbles would be deposited first. So I'll use my text tool and I'll write the word cobbles. And we're going to have to do something very, very interesting to get it. You can't turn the text boxes, but you can do that. It's just one way around the limits of this program. So right now, cobbles would be deposited closest to the mouth of the river, where it's emptying into the large body of water. And then what would be next on my list? Well, next on my list would be pebbles. Do I have pebbles in that listing? I certainly do. So again, use this, P-E-B-B-L-E-S. And now that would be pebbles, correct? So cobbles, then pebbles, then what would be next? Sand. So sand would happen next. So I'll click over here. Sand, type sand, not really writing it. And I'll position that into place. And then after sand, silt. So I'm looking for silt. Sorry. Silt would be there. And finally, clay. And so that's what the depositional pattern would look like. If you were swimming and had a scuba mask on, that's what you'd be able to see: cobbles, then pebbles, then sand, then silt, and clay. Now, they might be adjusted in terms of exactly where they are, but that's a rough estimate where that would be. So as the distance from the mouth of the river increases, moving from D to E, the particle size is going to do what? It's going to decrease. It's going to get smaller. The velocity of the river, what happens to it as it enters the lake? It decreases. Because the velocity decreases, so it's getting slower, the particles carried by the river will start to deposit. Sorry. That's when deposition is going to start, when the river starts to slow down. Okay, so let's finish with number 7. We're going to complete the graphs. Go to shapes, and then go to insert line. And here the particle size, as I go from D to E, my particle size is going to get smaller. I'll give you the degree measurement. It's kind of cool. So that's what happened there. And as I move from point D to point E, my water velocity would also decrease. It would be an indirect relationship right there. As I'm moving from D to E, my velocity gets slower as well. So now looking at the delta formation part of the handout, and you can see my Google search. Greek letter delta looks like a triangle, right? That's why they call it a delta, because that formation, that landform formation, looks like a triangle, hence the name. That's why they call it a delta. So if I take a look at the first number 8, which is not the first number 8, but 8, river deltas form from the process of, what process gives us delta formation? It would be the process of deposition. Again, you can see here, I want to make this a little bit bigger. Deposition. Cool. So the water starts depositing that material, and you can see here stage 1, stage 2, and stage 3. This is the process of developing a delta. You can see it looks like a triangular shape. As the river enters the large body of water, the velocity of the river, slows down. So that water molecules start to slow down. When slowing down happens, we get the opposite of erosion. We get deposition. Because that's water molecules slowing down, it's going to start to deposit. The first particle to be deposited would be blank in size. So we're just looking for the word large there. Okay. Now, as you move away from the mouth of the river, the spot where the river enters the large body of water, that's what they call the mouth, the particle size would, that's from previous ones, you should know that it would decrease. Okay. For example, at the mouth of the river, I might find, it wants you to name a particle. If I go back to my reference table, I could see boulders would be dropped off first, but it's very uncommon for a river to be carrying a boulder or even a cobble, but they can. Pebbles and sand and silt and clay. So you could put whatever you want for your answer there. The largest particle you possibly could put down would be a boulder, but I would say that's a very rare thing. So you could say cobble Nemo particle, and I would most likely find Nemo particle furthest from the mouth of the river. So furthest would be the smallest particle, which in this case is clay. So it would be clay. And that's what the stages are showing you over time, stage 1, stage 2, stage 3, and that is how a delta is formed. So here's another view of a delta from overhead, and tells you the diagram above shows an overhead view of a river delta in a large body of water. Answer the questions below. So I'm looking at question 10. The river entered the large body of water at what point? So wherever it enters the large body of water, the larger particles are going to get deposited first. So if the river entered at A, that would mean clay would get deposited first, then silt, then sand, then pebbles. We know that wouldn't be the case. If it entered at D, silt would just be deposited here, and you'd have other deposits on the side of it. It doesn't much make sense. But if we look at point C, that's where the river enters, and that's where I have the deposition of my larger particles here, which are pebbles. Then I have sand, then I have silt, and then I have clay. So the river must have entered this large body of water at point C. So I'm going to grab my text box, and I'm going to change it to, I think I want 18. I'm just going to put the letter C right there. Well, how do I know that? Because I said so. No, because at point, C, we have the largest sediments being deposited first, not first. Now, when it gets to this question, question 11, what is the minimum velocity needed to maintain but not start, see page 6 of the Earth Science Reference Table, particle B's movement? So let's, before we go to that page, letter B is a particle of sand. Now, the minimum, meaning will be the minimum. It says to maintain but not start. That seems a little weird in language, but we included this little diagram in the document. Relationship of transported particle size to water velocity, and in the little paragraph below, this generalized graph shows the water velocity needed to maintain but not start movement. Variations occur due to differences in particle density and shape. So this is just saying that's about the maintain part. What's pretty cool about this CAMI thing is if I do my shapes, and if I do them correctly, I could see sand is here, between here and here. So the minimum would be the smallest particle of sand. So that would be represented by this blue line. And now, what would be my velocity? I could do that in red, I guess. Where the two intersect, it's basically where I want to start my line. And bring it down to here. I almost have it at a 90-degree angle. Okay. So what I'm looking at now, you could see that's where those two intersect, about where they intersect, right? So if I look at my velocity, stream velocity, I have 0.1 centimeters per second, 0.2, 0.3, and then there's 0.4. So you could say anywhere from about 0.3 to 0.4 centimeters per second would be the velocity that would be needed to maintain, but not start. So go back to text box. So I would say 0.3. If you have 0.35, that's fine. If you said 0.4, that's fine. Anything in that range is totally fine. What particle shown in the diagram requires the least water velocity to maintain? Well, I would just take a look and I would just see right back here at this chart, I would see that clay requires the least. So that's a pretty straightforward question. So here I would write clay, or type clay. What particle shown would be deposited second by this river? So the first thing would be pebbles. The second one would be sand. So that's the overhead view of a delta in a river. And that's how you navigate these questions. So this is probably the jubilation that you're feeling after completing the delta handout. And What an incredible display of athletic ability. It's pretty impressive, actually.